Hello everyone, welcome to ME310 virtual class. As before, I have note posted on Blackboard and I will go through the same notes in this lecture. The ANOVA is a short name for analysis of a variance. So ANOVA is a statistical test that you use when you are comparing more than two measurements to each other. So that means that you can have 3 groups or you can have 30 groups, and you will still use ANOVA. Using this type of test, you can then compare whether there's a significant difference exists, and you can also say that what are those differences. One key assumption of ANOVA is that it assumes that all populations have a normal distribution. That means that if you have a non-normal distributed population that you're dealing with, you cannot use ANOVA, but these non-normally distributed tests are not part of this class, therefore we are not going to cover them. However, the techniques you use are somewhat similar. Okay, to do ANOVA, you have 5 steps, and this is very, very similar to our t-test. The first one is to develop null hypothesis and alternate hypotheses, right? So these are basically the same methods or same techniques that we use to set up our hypothesis. The only difference here would be that the null hypothesis will state that there are no measurable differences, therefore all the groups are equal to each other, and the alternate hypothesis will then say groups are different than each other, or in other words, the null hypothesis is wrong. In step 2, we will compute the F ratio, and F ratio is a measure of variance between means of different trials, right? So, and this is very similar to the t-score that we used in the previous 2 classes with the 1 sample t-test and 2 sample t-test. And this F ratio calculation is really the heart of the ANOVA analysis. Once that is done, we will find the critical value. Critical F value is analog to the T critical value that we have used in t-test. So that basically gives us a benchmark value that we will use to see whether there is a significant difference exists between means of each group. You can set this F critical value to 95 percentile, 99 percentile, or less. For this particular class, we will go and talk about 95 percentile, but the way that we do it is exactly the same, except you look for different values in the table. Number 4 is the comparison between the F ratio and the F critical value, which is exactly the same in terms of methodology to t-tests. If we found that the F ratio is bigger than F critical, we will reject the null hypothesis, and if the F critical value is larger than F ratio, we will accept the null hypothesis. And based on that accept and rejection, we will also do a post hoc test, which we will talk about later on. Okay, so the idea is that the null hypothesis, right, that the first step is based on the principle of no effect or no difference. That means that the null hypothesis will say that the groups are completely the same. So that's step 1. The F ratio is calculated by using the mean of squares between groups and mean of squares within groups. We divide them to each other. And we have never identified what the these mean of squares mean, so they are also further defined by for example, mean of squares, as you can see here, is defined as the sum of squares between groups divided by the degrees of freedom between groups, and that's divided by the sum of squares divided by within and the degrees of freedom within groups. These sum of squares between and within groups and as well as the degrees of freedom between and within groups are defined further at below here. You can also find this in your notes. A couple of annotations or couple of abbreviations that we use. SS here stands for sum of squares. DF stands for degrees of freedom, right? That's similar to what we used before. T is sum of all trials data points, and we will get to that. G is sum of all data points for all the groups and all the trials. X is the individual data point. N is the number of data points in a trial. K is number of trials, and N is the number of data points. So using that, you'll be able to use these equations to calculate the F ratio. So instead of going through these, what I will do is that I will set up an example, and then we'll go through examples step by step to figure out how can we do this. So let's say we had 3 groups and we had 3 different measurements, and these measurements we named x1, x2, and x3, right? You can think about them as accelerations that you measure in your lab, number 1, in x, y, and z directions, or you can think about the accelerations that you will use in this lab. So if that is done, we have used x1, which gave us the values of 0, 4, and 2, and x2 gave us the measures of 3, 6, and 6, and x3 gave us measures of 6, 8, and 10. So at the bottom row, I had taken the liberty of measuring the mean or calculating the mean. So the x1 mean is going to be 4 plus 2 divided by 3. That's going to be 2. Mean of x2 will be 5. Mean of x3 will be 8. So the when we say between trials, right, so that means that we are looking at different columns. So that means that x1 will be have different trials, x2 will be a different trial, and x3 will be another trial. And within each trial, we have multiple measurements, right? So x1 had 1, 2, 3 measurements, and x3 and x2 also had 3 measurements as well. So when I talk between trials, I talk about the columns, and when I talk within trials, I talk about rows. So now, if we have these measurements between trials and within trials, then I can set up my null hypothesis. That's number 1. And I simply say the x1 and x2 and x3 means are equal. So that means that there's no difference between groups. And the alternative hypothesis then says that H0 is not true, therefore there are differences between groups. And that will be the same for all ANOVA tests. So then the next step is to calculate the F ratio. To calculate F ratio, we will need a couple things calculated first. So we have T, which is sum of all trial data points. We have G, which is sum of all data points. K is number of trials, and N is the number of data points in each trial, and N is the total of data points. So T first is going to be the sum of trials in trial number 1. As you can see, trial 1, which is shown here by the red box, is 0, 4, and 6. Therefore, the sum of them will be 6. Similarly, the x2, which is shown by the green box, is going to be 15, and T of x3 is going to be 24. If I were to add all these together, I will find that G is 45. Number of trials that I have is 3. Number of data points per trial is 3, and the total of data points is 9. So the first thing I calculate is the degrees of freedom between groups, right? So that means that this is the degrees of freedom between groups. So I have 3 groups. It's going to be K minus 1. So that will be 2. And I call this degrees of freedom between, but I also call that a new one because one table that we'll look at very soon it calls this as new one, so you can then use that as a reference. And the second one we are going to calculate is degrees of freedom within trials. And I also designate that as a new 2, so you can use that designation as well. And that's defined as n minus k, and that simply gives us 6. Similarly, if I were to calculate the sum of squares between groups, it will be 54. And if I were to calculate sum of squares within groups, then it would be 22. And using that, I can calculate my F ratio, which will give me 7.36. So the next step is going to be to calculate the F critical value. And for that, I have a link here, which I also will be putting it into the comment section in the YouTube video. That you will find the F critical value by using new 1 and new 2 values. And the new 1 will represent the columns, and new 2 will represent the rows. Let me click to this link. And I will just carry over this momentarily so you can see. We are looking for a 5% significance, which is 100 minus 95 percentile, so it's going to be 95 percentile. And as we said, it's defined by two values, new 2 and new 1. And looking at our presentation here, we can tell that columns are new 1 and the rows are new 2. Let's go back and say that the new 1 was 2, so that will be column number 2 and the row number 6. Okay, let's go to column number 2. Okay, here. And row number 6, and my critical value is right here. That is a 5.143. So you can see that you can do it up to 10 groups, and you can do up to 100 samples. And so in that case, we go back to our presentation and look for our F critical value, which will be 5.14. And after that step, we will compare the F ratio to the critical value. The F ratio in that case, right, was larger than the F critical value. Therefore, based on the comparison, we reject the null hypothesis, right, with 95 percentile confidence, suggesting that there are differences between groups. So now, at this step, or at this particular point, we will be able to say that there are differences between groups, but we actually don't know which groups are different from each other. And that brings us to something called a post hoc test, right? So we will use a HSD test as a post hoc test, and if you will read the literature on this, you will find that there are a number of different post hoc tests that you can make, and this HSD test is very common and widely used, so it will be a good example of what a post hoc test looks like. And so the HSD test is simply stands for two keys honestly significant difference test. And HSD tests are used after ANOVA, right? And after we were able to reject H0, meaning that there are differences, but we don't know what is the cause of rejection, meaning that which groups are different from what groups, that the HSD test is going to be able to tell us. To do that, we will have to calculate something called an HSD value. An HSD value is calculated by mean of squares within divided by n in square root multiplied by a number called Q. Again, the Q is found by degrees of freedom within groups, right? Which is your new 2 and K. So I provided a link here, okay, and this will also be present in the comment section. I'm going to go there and let's see. So the K is number 3, okay, and our degrees of freedom within is 6, correct? And therefore, we are looking for a 0.5. And you can see that there's an asterisk here says that the critical values for Q corresponding to alpha is going to be 0.05 for the top and 0.01 for the bottom. Therefore, we are looking at the top value. So I'll go to degrees of freedom 6 within, and I'll go to K of 3, and therefore my Q value should be 4.34. Okay, and I will use that value 4.34 times the mean of squares within divided by the number of trials and number of data points in each trial, which will give us 4.77. So now I know what my HST value is. We will now look at which of the group differences or group mean differences beat this HST value. To do that, I will make a table with columns and rows are means of x1, x2, and x3, and I simply go and say x1 minus x1 is going to be 0, x1 minus x2 is going to be 3, x1 minus x3 is going to be 6, and x2 minus x3 is going to be 3, and all the other values will be just repeats of the same combinations. So in that case, any mean difference between groups that beat 477 is going to be designated as significantly different. Therefore, in this case, I will be able to say the group 1 and group 3 was a difference between group 1 and group 3 was the cause of rejection. In other words, group 1 and 2 was not different from each other statistically at 95 percentile. Group 2 and 3 were not different from each other at 95 percentile, but group 1 and 3 was significantly different from each other at 95 percentile, which led us to reject the null hypothesis based on ANOVA testing.